This is section 15.1. Chapter 15 is on multiple integration. All right, so page 988, 15.1, double integrals over rectangles. First, recall to approximate the area under the curve. Let's say here's your f of x from A to B. We chop the region into so many subregions. Pick a representative point. In practicality, the ones you probably pick were the left endpoints, right endpoints, or midpoints. But you could pick any point in between. This one looks like it's 1/10 of the way, midpoint, 3/4 of the way, midpoint, 2/3 of the way, and so on. And use that for an estimate for the area under the curve. So likewise, we can use something for volume under a function in 2D. So let's say you have a function defined from A to B for X and C to D for Y. Okay, again, you can pick a representative point. Okay, the points are all over the place, looks like. Okay, but you're basically going to end up with something like this. Okay, so here's a function, and your approximation is going to look something like this. So an approximation to the volume underneath the function. Now, again, in actuality, you're not going to pick random points. The most likely points that you would pick for any subinterval are upper left, upper right, lower left, lower right, or midpoints. Just like over here, you probably either pick the left endpoint, right endpoint, or midpoint. Okay, so our representative points would be those four: upper left, upper right, lower left, lower right, or midpoints. And as you might expect, the greater the n and m, n number of ways you're chopping up in the x direction, n number of ways you're chopping up in the y direction, the approximation gets better and better. Okay, so here's a function. We're trying to estimate the volume underneath z equals 16 minus x squared minus 2y squared. Okay, figure A, m equals n equals 4, so 16 high-rise buildings. Okay, here you have m equals n equals 8, so 64 high-rise buildings. And this is 16 times 16, 256 high-rise buildings. So clearly, this approximation of the volume is better than this one would be. Okay. All right. Okay, so midpoint rule, you could pick the midpoint. So here we're chopping the region 0, 2, cross 1, 2 into 4 pieces and pick the representative point to be the midpoint. So find the height, go base times height, base times height, base times height, base times height, add them up, a Riemann sum, just like it did for Calc 1. All right, we won't be doing too many of those. Most of the rest of the time, we'll concentrate on iterated integrals. Okay, where you integrate dA, a little change in area. You can either make it dy dx or dx dy. And this time, when I say dy dx, it's not dy over dx, meaning derivative. It's literally dy times dx or dx times dy. Okay, so you break up a dA into a tiny change in x direction, tiny change in the y direction. So it's either going to be dx dy or dy dx. And again, when I say dy dx, it's not the derivative that looks like dy divided by dx. It's dy times dx, like this. We have something called Fubini's theorem on page 994. You don't have to really write this on your cheat sheet, I don't think. But it basically says if you have the integral of f of x, y, dA, dA can be either dy dx or dx dy. Okay. When you have 3 variables, you have a dx dy dz as dv, a little change in volume, and we'll get to that a little bit later. Or you could have any combination, dz dy dx or dy dx dz and so on, so-called Fubini's theorem. So you integrate with respect to y and then x, or you can integrate with respect to x and then y. So here's a figure for each one. So here it looks like you're integrating with respect to x first and then y. Here you're integrating with respect to y first and then x. And of course, you would get the same answer either way. All right, so notice over here, if you integrate with respect to x in this picture at any particular value of y, it's constant. So you treat y as a constant. And likewise over here, when you integrate first with respect to y, you're treating x as a constant as you integrate. Okay. All right. So 15.1. So these. That's better. Just need to focus. Some more problems over here. Calculate the double integral. I don't think you have to do all of these, but I'll show it to you anyway. Okay. All right, so 15.1, page 999, number 1, z equals x times y. Okay, part A, looks like they're asking me to pick the upper right point of each rectangle. Let's take a look at the question. So number 1, z equals xy. X is going from 0 to 6, y is going from 0 to 4. Use a Riemann sum with m equals 3, n equals 2. So in the x direction, chop it up into 3 pieces. In the y direction, chop it into 2 pieces. And take each sample point to be the upper right corner of each square. Part B, use the midpoint rule. Okay. So here it is. Chop this up into 3 pieces. Chop this up into 2 pieces. So each rectangle is actually a square, 2 by 2. So the volume that we're approximating is delta A times the 6 upper right endpoints added up. So f of 2, 2, f of 4, 2, f of 6, 2, f of 2, 4, f of 4, 4, f of 6, 4. Okay, so delta A is 4. That's like delta x in Calc 1, right? So delta A is 2 by 2, 4 times, it's an easy function, it's x times y. So 4, 8, 12, 8, 16, 24, add them up, 288. Part B asks you to use the midpoints. So here are the 6 midpoints, 1, 1, 3, 1, 5, 1, 1, 3, 3, 3, and 5, 3. So V is approximately 4 delta A times f of 1, 1, f of 3, 1, f of 5, 1, 1, 1, 3, 1, 5, 1, and f of 1, 3, f of 3, 3, and f of 5, 3. Function's easy, it's just x times y. So it's 4 times 1 plus 3 plus 5 plus 3 plus 9 plus 15, 144. All right, then iterated integrals is pretty straightforward. Number 15. This means integrate with respect to y first, and then integrate with respect to x. Now, if you integrate with respect to y, that means you're holding x constant. So you go inside out. So integral from 0 to 2 dy, you do that first, and then it's nested, as it were. Integral from 1 to 4, integral with respect to x. So integrate with respect to y, 6x squared, y squared over 2 is 3x squared, y squared. Minus 2x is a constant, so negative 2xy. Y goes from 0 to 2. Then after that, integrate from 1 to 4 dx. Plug in 0, you get 0. Whenever you can do a shortcut, you should, because some of these problems get too long. So plug in 2 for y. That gives me 4 times 3, 12x squared, minus 2 times 2 is 4x dx. And now it's just an ordinary garden variety integral of one variable, so that's easy. So 4x cubed minus 2x squared from 1 to 4. Plug in 4. 4 times 4 cubed, 256. Minus 2 times 16 is 32. Minus plug in 1, 4 minus 2. 224 minus 2, 222. Okay, 19, integral from negative 3 to 3, integral from 0 to pi over 2, y plus y squared cosine x dx dy. So first I'm integrating with respect to x. So the 0 and the pi over 2 are with respect to x. And then the negative 3 and the 3 are with respect to y. Okay, integrate with respect to x. Y is a constant, so xy. Y squared cos x, y squared sine x. X equals 0 to pi over 2. Plug in 0, I do get 0, sine of 0, 0. Plug in pi over 2 y plus y squared sine of pi over 2 is 1. And now I integrate with respect to y. So pi over 2, y squared over 2 plus y cubed over 3, from -3 to 3. So plug in 3, I get 9 pi over 4 plus 9 minus plug in -3, 9 pi over 4 minus 9. Okay, the 9 pi over 4s cancel out. Final answer is 9 minus a -9, 18. 23, integral from 0 to 3, 0 to pi over 2, t squared sine cubed of phi d phi dt. Okay, so you might recall a little bit of Calc 2. Sine cubed, think of it as sine squared times sine, and sine squared, think of it as 1 minus cosine squared. Okay. Then I think of a u substitution. If u is cosine phi, du is negative sine phi d phi, so I put a -1 here and here. Change the limits of integration. If phi is 0, u is 1 by plugging in here. If phi is pi over 2, u is 0. So if the opposite of the integral from 0 to 3 and the integral from 1 to 0 of t squared 1 minus u squared du dt, but just take that negative and flip this. So 0 to 3, 0 to 1, t squared 1 minus u squared du dt. T squared is constant as far as u is concerned. That's going to be u minus u cubed over 3. As u goes from 0 to 1, plug in 0, you get 0. Plug in 1, you have 1 minus 1/3, which is 2/3. Take the 2/3 out, and you just have an easy integral of t squared. So that's 2/3 t cubed over 3 from 0 to 3. Plug in 0, you get 0. Plug in 3, you have 3, 9, 27 over 3 is 9. 2/3 of 9 is 6. Okay, 29, well, you could take your pick. 0, 1 cross -3, 3. Okay, so I decided to go dy dx, in which case x over x squared plus 1 is constant. Integrate y squared. That's y cubed over 3. Leave that alone. From -3 to 3. Plug in 3, you get 9. Plug in -3, you get -9. 9 minus a -9 is 18. Take out the 18. X over x squared plus 1, do a u substitution. U equals x squared plus 1. du is 2x dx. Put a 2 inside, half outside. Half combined with 18 gives you 9. So when x is 0, u is 1. And when x is 1, plug in 1, u is 2. So I have 1/2 times 18 is 9. Integral of 2x dx is 1 over u. And then, sorry, that's du. And then 1 over x squared plus 1 is du. That's 9 ln absolute value of u from 1 to 2. Plug in 1, you get 0. Plug in 2, 9 natural log of 2. Okay, 33. Integral over the region R of y e to the -xy dA, 0, 2 cross 0, 3. dA is a tiny change in area, which consists of a dx, dy, or dy dx. It's up to you. Okay, I decided to do dx, dy first. Okay, and notice this is kind of the chain rule in reverse. This is -e to the -xy. If you recognize that the reverse of the chain rule, think of differentiating this. If I differentiate this, I'd put the same thing down times -y, which gives me that. So when you integrate, you do the opposite. You lose the y and put the negative there. Okay, and then x equals 0 to 2 dy. Plug in 2, factor out the negative. So e to the -2y. Plug in 0, you don't get 0, you get -1. And I distributed negative, so negative, flip that around, 1 minus e to the -2y. Okay, so that gives me y. Integral of -e to the -2y is -e to the -2y times -1/2. So it's y plus 1/2 e to the -2y. So plug in, let's see, messed up all over here. So plug in 3, you get 3 plus 1/2 e to the -6 minus plug in 0, that's 0, minus 1/2. So final answer, 5/2 plus 1/2 e to the -6. Okay. 35 just asks you to draw a picture, so you don't actually have to evaluate, but I want you to get a feel of how the picture would look like for 35. So going 0 to 1, 0 to 1. So I just plug in 0, 0, 0, 1, 1, 0, and 1, 1. F of 0, 0 is 4. F of 1, 0 is 3. F of 0, 1 is 2. F of 1, 1 is 1. So there's real strange room where the four corners all have different heights. Okay, so 0, 0, 4, 1, 0, I go up 1, 2, 3. 0, 1, the height is 2. And 1, 1, the height is 1. So I connect these. So the bottom is nice, but the top is really weird. This corner, the height is 1. This corner, the height is 2. This corner, the height is 3. This corner, the height is 4. So you have a real strange room where the four corners here have different heights. Okay. All right, and then 37. 4x plus 6y minus 2z plus 15 equals 0. Negative 1, 2 cross negative 1, 1. Okay, so first you want to solve for z. Z is equal to 4x plus 6y plus 15 over 2. I factored out the 1/2 and integrate this. I just had to go dx dy. So x is negative 1 to 2, y is negative 1 to 1. Okay, so 2x squared plus 6xy plus 15x. X is negative 1 to 2. Plug in 2, you have 8 plus 6y plus 30 minus plug in 1, 2 minus 6y minus 15. Clean it up. You get 51 plus 12y dy. So 8 plus 30 minus 2 plus 15 is 51. And then 6y minus a minus 6y, 12y. Okay, so 1/2, 51y plus 6y squared from negative 1 to 1, which is 1/2. Plug in 1, you get 51 plus 6 minus a negative 51 plus 6. 6 cancels out. I have 1/2 of 51 plus 51, which is just 51. Okay, and then 41. Z equals 1 plus x squared y e to the y, negative 1, 1 cross 0, 1. So 1 plus x squared y e to the y dx dy. Integrate with respect to x. X plus 1/3 x cubed y e to the y. X goes from negative 1 to 1. Plug in 1. 1 plus 1/3 y e to the y minus, plug in negative 1 minus 1/3 y e to negative y. 1 minus a minus 1 is 2. That minus a minus that is 2/3 y e to the y. Can't have to take a time out. Integrate y e to the y. That's integration by parts. Let u be y. dv is e to the y dy. du equals dy. v equals e to the y. Remember, integration by parts. If you want to put the formula for integration by parts on your cheat sheet, you may. But it was uv. So uv minus the integral of v du. So it's y e to the y minus y e to the y plus c. Okay. So finishing it over here, integral of 2 is 2y plus 2/3. Integral of y e to the y is this, y e to the y minus e to the y from 0 to 1. Okay. Plug in 1, you get 2 plus, if I plug in 1 here, you have e to the y minus e to the y, which is 0. Minus plug in 0, that's 0. That's 0. That is 2, negative 2/3 times 1. So it's 2 minus a minus 2/3. Final answer is 8/3. Okay. All right. So that was section 15.1.